My name is Akhil Singh and my roll number is 20153103. So in this video I am going to explain about direct and indirect band gap semiconductors using EK diagram. So what is a band gap? So band gap is basically the distance between valence band of electrons and the conduction band. So it basically represents the energy electron requires to excite from valence band to the conduction band. Now what is a EK diagram? So EK diagram shows the relationship between the energy and the momentum of available quantum mechanical states of an electron in a material, and these satisfy the chronic Penny model, so these are not continuous in nature. Now what is a direct band gap semiconductor? So in a direct band gap semiconductor, the minimum of the conduction band and the maximum of the valence band align. So here from the figure we can take a look that at k equals to 0, the maximum, the top of the valence band and the bottom of the conduction band are aligned at the same value, that is k equals to 0. Now when a recombination occurs, that is when an electron combines with the whole of a valence band, the momentum change is not required, so it will directly flow from here to here and the value of k will remain same. So momentum change, there will be no change in momentum. So in a direct band gap semiconductor, no momentum change is required. Now when this electron falls from here to here, a photon is released. Now this photon has an energy of given by this. So basically the recombination will result in emitting of light will emitting of photon. So for this reason direct band gap semiconductors are using light emitting diodes. Now let's take a look at certain examples of direct band gap semiconductors. So these are certain direct band gap semiconductors and these are their energy band gap values. So for gallium nitride there is in EN is 3.4 electron volt. So these all are used in LEDs and lasers. Now indirect band gap semiconductors. So in indirect band gap semiconductors, the bottom of the conduction band and the top of the valence bands are not aligned. So for a recombination to occur, the electron will travel from here to here, which is certain deflection state, and then from that deflection state to the valence band. So for recombination to occur, this electron will travel from here to here. So basically in this process it will emit phonons, and then it will go from this conduction band to valence band and will release heat in the lattice itself. So recombination in this will radiate energy in the form of heat in the lattice itself. Now these are certain examples of indirect band gap semiconductors. So silicon, germanium, and these are their energy band gap values. So these are used in diodes and for switching application purposes. Now we have taken a look at direct band gap semiconductors and indirect band gap semiconductors. So in a direct band gap, so let's take a look at certain differences, key differences. So as we have taken a look that in a direct band gap semiconductors, this bottom and top of the valence band are aligned, while in indirect band gap semiconductor these are not aligned. Also in a direct band gap semiconductors, the photons are released, so that's why they are used in the making of LEDs, while in indirect band gap semiconductors this is assisted by the transmission of phonons. Also both energy and momentum are conserved in direct band gap semiconductors, but for indirect band gap semiconductor momentum is not conserved, as it will travel from that particular state, that is from here to here. So change of moment, there will be a change of momentum, so momentum is not conserved. Now the final point, the efficiency factor of direct band gap semiconductors is higher as compared to indirect band gap semiconductor. So for this reason direct band gap semiconductors are always preferred over indirect band gap semiconductors for making optical sources. Thank you.